Thanks a lot for the invitation. Let me say a bit about my talk. The point of my talk is to explore what we would lose if we replace significance tests with Bayes factors. I don't think that any one statistical approach encompasses every intuition that we have about statistical evidence in science, and so multiple perspectives are really necessary as checks on one another. And I think that as Deborah has said, that there is an important role to be played by classical and frequentist statistics in serving as a check on Bayesian statistics. And none of the things that I'm going to say here are really new. I'm going to contextualize them within a popular, currently used set of Bayesian procedures. And so the thing about this is that it's not as theoretical. We can always talk about how you can change priors and get different results. But, this is, in some sense, a lot of these discussions are theoretical until you get a real procedure that's used. And once we can talk about something that's actually being used, then we can talk about the practical consequences of having priors that have particular properties. I'm going to start by demonstrating what Bayes factors are, and then I'm going to talk about how Bayes factors under some conditions can show strong evidence for false null hypotheses. And this is really important because in some cases, null hypotheses may correspond to things like, is this drug safe, or something of this sort, where we really wouldn't want to say that there's no effect when in fact there is. Then I'm going to show how Bayes factors can show strong evidence for null, strong evidence for the null when the results are actually quite suspiciously small. So to begin, my data setup here to begin with, to show what the Bayes factor is, we have two groups of size n, normal populations, equal standard deviations, and an effect size of delta. So I'm going to use this delta. This delta is just the difference in means between the two groups in the two populations in standard deviation units. And I'm going to assume the stuff that we typically assume, like independence of observations, and that there's a fixed stopping rule. And so in this case, the evidence that we're going to use is a simple student's t-statistic. And that's going to measure how different our two groups are. So these Bayes factors that I'm going to show you are in use in a number of software packages. So my own software package here, Bayes factor, they've also been implemented in SPSS, in the software packages JASP and Jamovi, and they come from this paper here, a Bayesian t-test for accepting and rejecting the null hypothesis. The paper and the software have over 4,500 citations, and I'm not telling you that because I want to make my own work sound great. What I'm telling you this for is because these are in use, right? So the properties that I'm going to talk about are the properties of in-use hypotheses. And I'm also telling you this because I don't want you to think that I'm just bad-mouthing somebody else's approach, right? This is my software here, Bayes factor. These are techniques that I helped develop. And so I'm not just rubbishing somebody's work. This is my work. But I think it's important that we examine all of the statistics that are in use and we talk about their properties. So let's start out by thinking about likelihood ratios. So in the last talk, we already saw a bit about this. So imagine that we have a true effect size. We're sort of considering two possible true effect sizes, one that is delta equals 0, and then one that is delta equals 0.3 standard deviations. And so what I've shown you here is two curves that represent our predictions for the t-statistic from those two different effect sizes. And so this is our familiar student's t-distribution in red here. for a sample size of 20 people in each group. And the blue line is what you'd see for the t-statistic if we had an effect size of 0.3. And if we saw a t-statistic of -1, you can see that that would be much more common under the null hypothesis of delta equals 0 than under a true effect size of 0.3. And this ratio of the two densities we call the likelihood ratio, and that's about 4 to 1. So we would say that our likelihood ratio, when we saw a t-statistic of -1, comparing 0.3 to 0 is 0.25 in favor of this alternative hypothesis that delta is 0.3. So because this is less than 1, we say it favors the null hypothesis delta equals 0. Now we can, of course, do this for all of our t-statistics. And what we find is that as t gets larger, we favor the delta equals 0.3 relative to the null more, because those would be more common. Those large t-statistics would be more common under the hypothesis of 0.3. And likewise, as we get smaller, the smaller t-statistics would be more common when the null hypothesis is true. If we were to consider a larger effect size against the null, we get different likelihood ratios, right? So if we were to consider delta equals 0.5, because these two hypotheses are more different from one another, we get larger likelihood ratios when the t-statistic is large, and smaller likelihood ratios when the t-statistic is small. So we immediately see a problem here. We typically want a composite hypothesis, but every one of these lines that we could draw would only compare one of these deltas to the null hypothesis. So we'll address that in a second, but let's think about likelihood ratios in general first. So frequentists is happy to use likelihood ratios. They can, as test statistics, they can be justified through the Neyman Pearson lemma, which shows that you can get a high-powered test out of these, which is really nice. And what's important is that their interpretation is through the error rates of tests, right? It's not a direct interpretation of the likelihood ratio. Now, a Bayesian says, actually, no, you can use the likelihood ratio as a measure of evidence. And this comes directly from Bayes' theorem. So the interpretation of these numbers is direct in terms of statistical evidence. That ratio is statistical evidence to a Bayesian. Why is this the case? It's the case because in the middle of Bayes' theorem, you can find the likelihood ratio in the move from what's called the prior odds to posterior odds. Now, a Bayesian would say, actually, typically we have uncertainty in the parameters in our models, and so we have composite hypotheses. So what we need to do is we need to average across these parameters, in a composite hypothesis, and get an average probability of the data under specific hypotheses. And then we compare these average probabilities, and instead of a likelihood ratio, we have a kind of generalization of the likelihood ratio, which is the Bayes factor. The ratio of the average probability of the data or density of the data under two different models. So we might have model 1 in the numerator and model 0 in the denominator. And so this gives us a comparison between two maybe composite hypotheses if we like. It could be a null hypothesis and a composite. It doesn't matter. What matters is that we averaged across the uncertain parameter, and we averaged across the prior, which is really important. So we have a prior distribution, which represents what we think this parameter might be, this parameter value might be, if that model is true. So why are Bayes factors advocated by Bayesians? There's a number of reasons. I'm going to go through these pretty quickly because it's not my purpose in this talk to defend Bayes factors. But to a Bayesian, it's nice that they have a direct interpretation as statistical evidence in terms of convincingness, a move from prior to posterior, the degree to which the data move you, which is quite nice, that direct interpretation. Bayesians also talk about the ability to show evidence for point nulls, which is not a feature that you will get from a typical significance test. And this is nice to a lot of scientists because this gives you evidence for regularity, evidence that means are the same. This is something I'm going to focus on later, some of the challenges here. You'll often notice then in psychology, at least my field, you'll see a lot of the advocates of Bayes factors are statistical modelers. And this is really important because statistical modelers in psychology are often comparing different kinds of models to one another, and they're not nested within one another. So the Bayes factor allows you to compare whatever two models you like, as long as you have some sort of priors over the parameter space. And so this is really important. And I think this plays a role in why you see certain people advocating Bayes factors over others. Model selection consistency in the large sample limit. So if you get more and more data, you will eventually select the model for any amount of evidence that is true, as long as it's in the set of models that you're looking at. There's also these other ones, perception that p-values overstate the evidence, insensitivity to stopping rules is seen as a benefit. And so for all these reasons, Bayes factors have been suggested as a replacement for p-values. Now, there's two main properties of Bayes factors that I'm going to talk about. One is that they're marginal. Bayes factors compute the probability of data by averaging over the prior, and this is very different from how a significance test works. Now, the criticism of this that you could levy here is that averaging over a prior can lead to high error rates for some elements of a hypothesis, and I'll show you how this can be the case. And this leads to what you might call a lack of severity. You have a high probability of claiming evidence for a false hypothesis. And then the second feature of Bayes factors is they're comparative. They compare one model to another. And so both models might be obviously terrible. And so you have this issue that high probability under one hypothesis may actually be suspicious. That is, it's too good. And Bayes factors offer, or likelihood ratios, offer no account of this, in spite of its importance in statistical forensics. So we'll talk about that a second. One thing that in a lot of the workshops I give about Bayes factors is you always get this question, what's a good Bayes factor? Like, how big does a Bayes factor have to be? Which is funny because we're supposed to be able to interpret Bayes factors directly, but this is always a question. How big should a Bayes factor be? Now, there are a number of guidelines that different authors have given. Jeffries in 1961, in his 1961 book, suggested these, that I'm going to focus on two here really, that are important. So a Bayes factor of, well, three. A Bayes factor of 1 means that you have equal weighting of both models. Now, Jeffries suggested that a Bayes factor above about 3, or from 1 to 3 is barely worth mentioning. And then you get substantial evidence between 3 and 10, and strong evidence is anything greater than 10. And then you have some other categories above 10. Now, 3 is important because this has been suggested by some Bayesians as being sort of equivalent to 0.05, a p of 0.05 under some calibrations. Now, I'm going to focus on 3 and 10 because 10 is this boundary between substantial and strong evidence. So let's start with data prediction. So I already showed you a bit of these. Let's suppose we have 78 people in my two groups. This is what the t-statistics would look like if I had a true delta of 0.5. I would expect to get t-statistics in the 1 to 5 range. But of course, delta equals 0.5 is not my only possible effect size. I could have effect sizes that, if I'm thinking about non-zero effect sizes of, well, anything, right? So what I'm going to do is I'm going to put a prior distribution across these different effect sizes. And this is the default one that's used in the software that I showed you. It's a T distribution with 1 degree of freedom. You can see that it weighs the small effect sizes heavily, and the larger effect sizes get increasingly less likely. This is it has a scale, this T distribution, 1 degree of freedom, or a Cauchy distribution of 0.707. So square root of 2/2. Why 0.707? So this, we started in the paper that I showed you with a scale of 1, and because I was the author of the software, I decided to change it to the square root of 2/2. And you know, if you know something about statistics, you know how these numbers kind of just become defaults if you do something like this. And so this, a lot of people don't change this, and a lot of people just use this as the prior. So I will use this in my demonstrations, the default prior that I've selected, just because that's what's in use. So some people may have a justification for using this default, some people may not, but I made it up. So that's something to think about with respect to these procedures. Now, if you look at this curve, you can see I can put on the effect sizes that I had in the last slide here, and you can see that the ones near 0 are more likely, and the ones away from 0 are less likely. And so what I'm going to do is I'm going to take those data predictions and I'm going to weight them by the prior. And so when you do that, you get a distribution, you get multiple distributions over the T statistics. And so you see that they sort of cluster around 0. And when I average across when I average across these effect sizes, what I'm going to get is a distribution called a prior predictive distribution that is spread out across the T statistics according to this sort of average across the different effect sizes. So this is my average prediction across the prior for where that T statistic will be if my effect size has that distribution. Now, it will be affected by the sample size, of course. If I have a small sample size, I will have smaller T statistics. If I have a larger sample size, then those big effect sizes, of course, will lead to larger T statistics. And so my distribution will be more spread out. So this is how we end up, well, I'll show you in a slide. This is how we end up getting a Bayes factor. So what might we select as a prior? Well, there's lots of things that we could do. This is my default that I showed you, but I could have other distributions as well. I could do whatever I wanted, but this is what we suggested in our paper, that you can sort of scale in or scale out the Cauchy distribution in order to predict smaller effect sizes or larger effect sizes. And so this red is the default that pretty much everybody uses. The initial default that we suggested is this 1 here. And then I'm showing you what happens when you multiply the scale by 2 or divide the scale by 2. So you can see that you can, scale out this prior or bring it in if you like. So I'll show you some properties as we change the prior. And then we're going to compare the average data under one of these priors to what happens under the point null. So what you see when you do that is you take your prediction over the T statistics, which is averaged across all these alternatives. And then when the point null is true, you have a student's T statistic. And you can see that you can just take the ratio, and that tells you how much you support one hypothesis over the other. It's a likelihood ratio. So in this sort of orangish region, I am favoring the null hypothesis. That's about a T statistic of -1 to 1. I'm favoring it by 3 or more inside of this region. And when the T statistic is more than 2.5 or so, or less than -2.5, I have a ratio of greater than 3 for the alternative. That is, that there is some effect averaged over the prior. And this is with a sample size per group of 78. So that is the marginal prediction for the data under two hypotheses and how we use it to construct a Bayes factor. Now, in order to get to my critiques, I'm going to give you a slightly different data setup. I'm going to move from 2 groups to 4 groups of equal size n, and our effect size is now going to be omega squared, or the proportion of non-error variance. Now, the reason why I didn't do this with 4 groups, I didn't do the demonstration with 4 groups, is difficult to do graphs in, in this case, 3-dimensional space. So I stuck with the easy case, and now we're going to go to a slightly more difficult case, but this is just one way ANOVA. So we have omega squared as our true effect size, the proportion of non-error variance, that is the variance in the means, and otherwise it's the same setup. We're going to use the F statistic as our evidence. And so here is, for 2 effect sizes, what the distribution of whatever measure we're talking about is. So for omega squared equals 0.01, this is kind of what it would look like in terms of the difference between the means. This is, in psychology, what is often considered a small effect. This is considered a medium effect, an omega squared of 0.06. What do we get in terms of evidence for the null from different F statistics? What I'm going to do is I'm going to show you on the x-axis here the F statistic in 3 plots, and these 3 plots show you for different sample sizes what the Bayes factors look like. So these are increasing sample sizes. I've denoted strong evidence in either direction. So up here is strong evidence for the null. Down here is strong evidence for the alternative, that is, there is an effect. And I will show you 4 prior scales, including the default one, which is here, the red 1/2. Here we see that the maximal evidence for the null happens when F is 0, and when F is 20, we get something like a Bayes factor of 10,000 for the alternative, and between 0 and 5, we have sort of what you might call equivalent, and certainly not strong either way. And we get more evidence when we, for the smaller F statistics and the larger F statistics, as we increase our sample size, which makes sense. This is affected by our prior. So you can see here, if we change the prior by multiplying it by 2 or dividing by 2, we get different Bayes factors because that changes the prior predictive. So now what I'm going to show you is what happens with the different effect sizes that I showed you in terms of your error rate for accepting the null hypothesis. And accepting here means you get a strong Bayes factor, or a Bayes factor that is 10 or greater. So this is considered strong evidence. So if my effect size is 0.01, and then I'll show you the typical error tolerance here, 5%. So we typically don't like to go above 5%. If the prior scale is the default prior scale, and you have, say, 50 people in each group, and the true effect size is 0.01, you have a probability of roughly, say, 40% or so of falsely accepting the null hypothesis if the effect size is 0.01. Is this important? It depends, right? But people should know that this is a rather high error rate here. Now, if the effect size is a medium size effect, you're unlikely with this particular prior to falsely accept it. But if you were to change the prior by a scale of 2 in one direction, you could have an effect size or an error rate of 75%. And then even for a medium size effect, you could have an error rate above 25% for accepting the null with strong evidence, right? And don't get hung up on the idea of acceptance here. You know, you don't have to literally accept the null here, but you're saying there's strong evidence here for a false hypothesis, and this is really important. You should be aware of this if you're using these methods. This is the result of marginalization. So the probability of data is averaged over large effect sizes, and so small observed effect sizes look null. And a frequentist would say this shouldn't be possible. You should protect from these high error rates by maximizing the probability, not averaging, right? So the p-value will maximize across the null, not average over your hypotheses. And so you can guarantee the error rates are controlled for every parameter value, not just on average. Now, a Bayesian, in order to defend this, will say, well, you got to have some sort of priors, and Bayes' theorem says that you have to average over them. But they might also defend conservatism in general. Like this is, you want to have acceptances of the null. This conservatism is good. Because a lot of the problems that we see in the replication crisis are of the sort that we're saying that effects are real when they're not. So conservatism is good. But I always go back to this example of, if you're a drug company and you want to say that drugs are safe, you want to accept the null hypothesis. A high error rate in favor of saying that two groups aren't any different in terms of their bad side effects would be really nice for you to be able to say, sure, we're going to accept the null hypothesis that this drug is safe. You could also appeal to parsimony, and you can say that this sort of, it's good to accept the null hypothesis when you have small effect sizes. That's possible, but you should be aware of the large error rates. So the last thing I want to do is talk about too good to be true nulls. So what happens when the F statistic or the T statistic is really small? When that happens, people start to get suspicious. And this happened, if you're aware of the Fisher-Mendel controversy, where Fisher accused Mendel, well, Mendel was dead at the time, but Mendel of, with his experiments with pea plants, of having results that were too close to his theoretical predictions. So this was a huge controversy. It's fascinating to read about. And Edwards has a nice paper in 1986 where he recaps this, and he says, this is the problem. If it were just a question of hitting the bullseye with a single shot, we might conclude that Mendel was simply lucky. But when a whole succession of shots comes close to the bullseye, we're entitled to invoke skill or some other factor that is cheating. Now, this logic is used in statistical forensics. If you're familiar with a fraud complaint against Jens Forster just some years ago, in this report, they say, our results suggest a level of linearity. So if you look at his data, you'll find that the effect sizes in say a 3-group experiment tend to be too linear. And this happened over and over and over again. This level of linearity was extremely unlikely to have arisen from standard sampling under the null hypothesis of linearity. Any actual deviation from perfect linearity would even lower these probabilities. So these were too good, right? These too good becomes suspicious. Now, frequentist doesn't have a problem with that because they can say, well, it's very unlikely to see test statistics so close to the null, particularly over and over and over again. That's significance testing logic. But a Bayesian or a likelihoodist has to invoke something else. And so Edwards says this: any pattern which we recognize in some data which is unexplained on the current hypothesis is a signal we should seek an alternative hypothesis, because an alternative which accounts for it is almost bound to have a higher likelihood. But the question is, why were we suspicious in the first place? Because the hypothesis had very high probability under the null hypothesis, right? Why are we suspicious of that? And what I'm going to do is I'm going to show you Bayes factors for data which would lead to an empty confidence interval. That is, they're so small that they lead to an empty confidence interval on omega squared. That they're small, as small or smaller than 25% of F statistics under the null hypothesis. A Bayesian procedure simply says this is a lot of evidence for the null, even though it's suspicious. And with larger sample size per group, it's even more evidence for the null. And it makes sense from a likelihood ratio perspective, but why are we suspicious of these? A comparative account can't actually tell you why we should be suspicious of that. So just to wrap up, I want to say Bayesian marginalization and comparative evidence lead to radically different results from statistical significance testing logic in certain cases. So in terms of marginalization, what can happen is you end up averaging across a whole range of parameter values. And so we can claim strong evidence for a null hypothesis that is false because we've averaged across very large effect sizes. Now, this, of course, flips Benjamin et al.'s 2008 argument on its head. Bayes factors, not p-values, can make it easy to find misleadingly strong evidence. You scale out that prior, and you're going to find even more evidence for the null. And this is due to the marginalization. So you really need to look at the properties, the frequentist properties of the procedures in order to see this. Secondly, suspicious nulls are considered strong evidence for the null because of the comparative nature of them. And if you are not tuned into the comparative nature of Bayes factors, you might say, well, everything's fine. This is strong evidence for the null. But actually, you might want to be suspicious of results that are too good to be true in the null direction. And if you lose that, the grounding for that claim, then you've lost an intuitive forensic check. And even Edwards, in his review of what Fisher did, had to say, you know what, I'm a likelihoodist, but still, you know what, Fisher's conclusion that Mendel was cheating, I can't find a problem with that, in spite of the fact that he was depending on significance testing logic. We can't lose that, the logic of these forensic checks. And we would, if we were to replace p-values with Bayes factors, we would lose those things. And so it's really important that we keep frequentist checks on Bayes factors. And we don't want to replace one with the other. And that's all I have.